All right, so this week's seminar speaker is Dr. Jupiter Hansen, who is a visiting assistant professor at Appalachian State University. She is a planetary geologist focusing on structural geology and tectonics. And so thinking about fractures and faults on planetary bodies and characterizing them to learn more about the history of their surface, but also potentially their subsurface. She got a bachelor's degree and master's degree from Hong Kong University, and then actually did stuff on Venus.
Yeah.
And then went to the University of Georgia, which is not that far away, to do her PhD, focusing on Ceres and Vesta. And like I said, now she's up at Appalachian State, and so she drove down yesterday, and I'm happy that she's here joining us today. So with that, floor is yours. Yeah, thank you so much.
Thank you so much. There we go. So thanks for having me today. I'm very excited to tell you some of my work that I did for my PhD, which I finished just last year. So it's still very fresh. So again, my background is basically like very geology focused, mainly on structural geology. And like I also do like rock mechanics too. So in the talk today, I'm going to focus on the origin and growth of fractures in a low gravity body. And as a geologist, I always emphasize on how we should look at rocks on Earth first, and then apply it to other planetary body. For example, like Vesta. That's what I'm going to talk about today. So here is just to thank multiple organizations that fund like my trips and my research, and also like App State and also Georgia that actually paid my salary for me to do my research. I have like two undergrad research assistants. So Jay, he went to Hawaii with me, so you will see a lot of like few pictures that we got Hawaii together later on. And Dave is that do some like credit accounting work on Vesta, which is also not entirely presented, but like used in the conclusion for this presentation today. And a cool thing about studying asteroids is that you can get an asteroid named after you. So that's very interesting. So first of all, I want to, spoiler. I'm gonna use that. So first of all, I'm just going to show you these amazing structures that you probably have seen a couple of times if you take a geology class, or just look at your Windows wallpaper. So we have like ripstones from like Iceland, and then there's like San Andreas fault in California, and here's another like strike slip fault there in China. So it is like either at the plate tectonic boundary or like related to plate tectonics. That's why we have these amazing structures that we know that, oh, the outer shell of the Earth is like breaking into different pieces. It is moving. It's really dynamic, still active. But we also, when we look at planetary surface, you also have these amazing structures, basically in a lot of planets. So for example, like Mars, bigger ones and smaller ones, our neighborhood like Moon, you have this Graben in here. And even smaller ones like Phobos, like you still have these like linear structures, and Vesta, which you will learn a lot about it today in my talk. And even for Europa, it's icy, it's not even like rocky, but we still see the structures in here. So my big question is, how are the structures formed on planetary surface without plate tectonics? When a lot of things that we see on Earth is about plate tectonics. So what happened? So in particular, what are the processes and mechanism? And my big question is, how are they different? As you can imagine, there are different parameters. As I said, some are like rock, some are ice, and some like even the rock itself have different properties. And today we're mainly going to focus on like gravity, like how gravity will change the type of fractures that we see. So as an introduction, I would like to give you a little one slide introduction for structural geology class. So what happened when there's like extension in the lithosphere? So extension means that things just look sideways, right? So in here, you have a block diagram. So there's like where you will stand on, so that's the surface. And then here is the subsurface. Here's a little chart here. So from zero, depth here, that's the surface, and then to depth. And let's say at the near surface in here, in the extension, you have like tensile stress. That's basically just like pulling the rock to the opposite direction along the horizontal. So in here, that's the tensile stress and I plot. So the more to this way, the more tensile. it is. And then it goes to 0 here, and then on this side, it's more like compressive, so things like push together. So if your tensile strength here exceeds the tensile strength of the rock, then it just opens up, it cracked, it just opens up. So that's form what we call jointing in here. But when it goes deeper into the surface, now you have what we call overburden pressure because of the weight of the rock, and also not just like from the top to the bottom, but also at the surrounding. It's like, at the middle of the ocean, right? That you have pressure all around. That's the overburden pressure that increase from 0 at the surface all the way down, depends on how deep it goes. That insert a stress. Now you have the top and the bottom, the vertical, you have the compressive that's pushing towards one another. And that also counters the tensile stress that is going like horizontal. So now you have a smaller one here. But if the tensile stress is still exceeding the strength of the rock, which is usually pretty small for a rock, then you still have jointing that it just opens up. But later on, when you go deep enough, that you have all the overburden pressure that is shifting the tectonic stress from tensile entirely to compressive. So now you have the vertical one is basically the entire, like just the overburden pressure, but now the horizontal one is a smaller compressive stress too. It is still extensional because it is smaller compared to your surrounding. But instead of opening up, now you have all the stresses pushing together, so it slides, so it just forms faulting. So from this case, we can see that like on Earth for like big rift zone, which is what we're gonna see in Hawaii today, we have those big openings there. And then you have like this side is higher and this side is lower. So that shows you, that's the sliding occur at depth too. So in here, we can see the gravity, which is basically what we talk about, the surface gravitational acceleration of a planetary body controls what type of fracturing behavior that you will have in an extensional tectonic regime. But what about smaller planetary bodies with a lower gravity? So if you think about like the size of the Earth compared with the size of Vesta and the G here, Vesta have like around 45 times lower like gravity compared to Earth. So we probably would expect that will be different type of mode that it affects and what we see on Earth. But to understand how this process occur on Earth, we can not only focus on the big structures here. When we go to the field, we start from the really smaller ones. So like here is just a pure joint that's like smaller, that's the ruler as the scale, that it just opens up. It's from the top view. So you can see the opening, like what we call the aperture here, that's like the maximum in the middle, and then it tapers towards the two ends. And then later on, they form this zigzag pattern because it is Hawaii, so you have a lot of basalt, right? So when basalt cool, you form this hexagonal shape of like pre-existing fracture. And later on, those joints take up those fracture and form those zigzag patterns in here. And then when they grow more, there's two joints that like interact with one another. And then eventually it goes bigger and bigger to the structures that we will see. So here, that's basically Big Island of Hawaii. And at this region here, you have the Kilauea volcano, which is still really active. Even when we're at the field, it is erupting. So that's pretty cool. And then you have the two rift zones on the side, and then this fault system here. So what's going on is because the volcano is still very active, so it's like building in elevation that lift the two sides of the rift zone up. But on this side, it's basically just facing the ocean. So there's no support on the other side. So things are actually just falling at its own weight towards the ocean. So you have an extension that is kind of from north to the south direction in there. And then that's a closer view of my field area. So we have this really long fault in here, and then like two pretty big one, but like relatively smaller one in here. That's so more like at the back in here, but because of the time that where we go, it's like not really accessible because of fire danger and things. So we basically focus on these three main faults and also the smaller structures that is associated with it. So I'm going to bring you to the field now, and then we're going to start with the biggest structures first. So here is the structural map is going to build up like once we go through like different structures in here. But that's basically how I map the largest fault in here. So let me show you some few pictures first. So when we're at this location around this region in here, so more or less in the middle, We are standing here looking at the south. So we're facing like this direction, like the volcano is at the back. And then we see this like massive vertical like fault scarp. And then you can see, there are different structures, this kind of like subparallel in here, and then the hexagonal patterns from the pre-existing fracture on the basalt itself. So then we mark the place that we're standing on is what we call the hanging wall, so like the down-dropping block of the normal faulting here. That's why it's indicated by the little box symbol on the map, and then we're standing on this side of the faulting here. So that's pretty simple. We don't really see any opening in here. We just see, it seems like, all the rocks here like collapse into, like filled in the basement of the fault scarp. And then when we walk more away from the center of the fault towards the tip, now we see there's like a little other curvy structures that is going from the lower hanging wall towards the footwall side. So that's what we call, literature is called monocline. So it's basically, it's a flat top there and then it gently dips towards one side. It looks really eroded. We feel not really safe to step on it. And so, but we also like just walk around and then we take measurements of the width and the height of this pretty collapsed monocline structures. As you can see, the gray shaded there, it's basically where we see the structures when we walk along the faults. And there are other features, for example, there's like a relay ramp that the two faults intersect with one another. And also there's like really just a massive like joint and fault, smaller ones that is at the tip of the fault, which is pretty typical. And there's like some pits here too that really got us in the field. So be careful when you go there. So next we're going to look at still big fault, but relatively smaller one. That's the O'Hare fault and also the Right Rabbit fault. As you can see from the map, they are also facing, the fault scarp is still facing the north, so towards the volcano in here, which is the same as the largest faults that we see earlier. So they have a very similar morphology. So when we're in the field, we are like standing at the lower part of the monocline in here. Now we can see the vertical fault scarp and also a more intact monocline that is like going all the way up, like almost towards the top of the fault scarp in here. And it looks more intact, so we feel more safe to just walk on the monocline. So here that we are taking a picture from on the top of the monocline and then looking into the faults, now we see that like an obvious opening, like in front of the fault scarp. And there's like also like elevation in between, not just where we stand at the base, but also for the monocline itself. So to have a little sketch in the field to digitalize it, it's like that's where we are at the base of the monocline. And then we have a monocline here. The basement, like in between the opening is actually pretty filled. So we don't know how deep it is. We don't really know what's going on, but it is definitely an opening in there. And then there's the relief of the fault scarp. And also usually at the footwall, so like behind this part, that's basically like big subparallel joints in there too, so just the opening. So we take measurements of the opening, the relief of the fault scarp, the width of the monocline, and also the height of the monocline along the way. And next, of course, we have to look at some smaller structures along the way too, so we can see like how the whole process is from small structures to big structures develops. So here in total, we mapped and detailedly measure like 50 pure joints. Again, pure joints meaning that we just have the opening. The two sides looks about the same in elevation. So we have a really small one in here. It's about like 20 centimeter. Or the smallest one in here that is connected to other structures, and the really big one in here. I think we measured in the field that the length is about like 800 meters that we use the tape to measure, which is really challenging because it's super windy at that time. And also like it's very hard for us to cross because it's like several meters opening, right? So we have to find a way to like get through the whole way in there. And we have like 26 shear joints. So basically like the first image that I showed you that you don't really have a monocline, but you have a big opening and some sort of elevation different on both sides. So that's why we classify it as shear joint. It's like, okay, there's probably some sort of sliding and faulting occur beneath, but mostly what you see is the opening from the jointing itself. And of course, as a geologist, we cannot just go and look at the structures, we have to look at everything that is like surrounding us. So of course, there is like so many lava flows around, And here shows you a picture. This is basically part of a monocline, and then the fault is at the back. And we see this pattern of like lava flow that seems like flowing up, which is kind of weird because it should go from a high ground to a low ground. So what we're thinking here is originally, this part is probably like higher in elevation and then flowing into the picture here, that's a lower ground. And later on, you have the faulting event occur that forms the monocline that tilt the lava flow in the opposite direction. And that's kind of consistent in what we picture, like we see most of them is like, you have this two lava flow that's supposed to be together and then like cross-cut by the fault itself. So we deduce it is still a very active like tectonic event happening in here that it's like younger than the last like lava flow event that occurred at that region. So here it's the entire map, and we collect the data that I just mentioned in around like more than 200 GPS points along the field, so you can see our trace along the faults from the GPS data. And then here is like part of the measurements that we have that is like too much that we cannot include it. I think in total we take like 1,000 measurements in the field for the 2 weeks. So if that's a fault, we take measurements of the opening and also the relief. If that's a monocline, we take the height and the width of the monocline. If it's just a joint, then we take the opening of the joint. And again, most of the structures, we can actually measure the length of the structure in the field too, except for the big ones, then we basically like mainly trace it by ArcGIS with remote sensing data for the lengths. So here, I'm going to summarize in block diagram of what we think is going on in the field. So first of all, especially when we look at the minor and smaller faults and joints, we think that it should be like jointing at the beginning, so it initiates at the surface. And then sometimes you have those shear joints that faulting start to occur at depth. And again, they are all in those zigzag patterns because you have the pre-existing fractures from the basalt cooling. And then when it further develops, you have bigger opening, a bigger relief now, and then the monocline start to take into place this forms this curvature from the faulting, and that's still the opening and also the relief that you can see. And then later on, when it gets like bigger and bigger, with the opening, the interior of the monocline start to be unstable. So things collapse in there and just leaving, some of the slab in here, and then some of the area you can see like entirely collapsed. So we can like just look into what's going on with the interior of the monocline. We have like some big joint at the back of the footwall in there too. And for the bigger structures, for example, like the largest fault that we see at the beginning, now we see the whole picture, we think that, it's probably, it was a monocline there, but it just entirely collapsed in there. That's why you don't see any openings. You just see the base is like filled with like rock fragments and very broken stuff. So that's what we think that's going on from jointing to faulting, and then there are some little bit more complex like morphology that comes in. And that does not just show you like step by step how it forms, it shows you continuous morphology along the structure. So you have in the middle of the big structure, it's just entirely collapsed. And then more and more towards the tip of the joint, things are more intact with the monoclines. And then we see the monocline goes away and just leaving like subparallel smaller faults and joint. That's basically the damage zone at the tip. So after we see how gravity on Earth controls, you have both the opening at the beginning and then the sliding later on. The next part is how do we apply to planetary, which is something that we're really interested in. So here I'm introducing you Vesta. So of course, Vesta is the biggest asteroid, but the second largest body in the main asteroid belt because we have Ceres, which is a dwarf planet. And one important thing about Vesta is I think it's still the only small body, like for asteroid that we found is differentiated. So it's like a core, mantle, and a crust. It's probably not active. It's like so small, it's probably entirely cool. I would be really surprised if we detect like, still active like lava like motion down there, but no, it is differentiated. So at some point it is hot enough for it to melt inside. And so Dawn mission in 2012 went there and then like captured this picture, and so as like a lot of other data set here. And then as a structural geologist, I care about what is on the surface, like the structures. So instantly I can see that there is this like equatorial troughs that we call the folia fossae, and there's a northern trough here that it's like a little bit tilted, and you only find it at the northern hemisphere. That's the Saturnalia fossae, and then there's kind of like cross-cut or like truncated by the equatorial ones in here. And then we have the Resilvia basin, which is like, this is like the rim, so the whole like southern hemisphere, it's like basically like big part of it is the impact basin itself. And then we have the Bananea basin like at the back of it that is like superposed by the Resilvia basin. So I have a little 3D print model in here, so you can take a look at it. The trough may not be as apparent if you just look at it in this direction, but if you tilt it and then see, you know, like at this angle, then you can like kind of see the shape of the troughs at the side. So you can pass it around to see how dramatic those structure is on such a small body. Let me give you a little estimate. So for example, like this, like Vesta, the diameter is about like 530 kilometers in diameter. But the size of this trough is basically the size of the Great Canyon. So it gives you an idea about like how big they are. So my question is, what are the types of fractures that you see that form these troughs, and how are they different from what we observed on Earth? So after the Dawn mission, there's like previous hypotheses that study the morphology of the troughs, and then they found that most of them are flat floor shaped. That's why it's concluded, oh, it's probably grabens formed by normal faulting. So meaning that you have like two normal faults dipping towards one another, and then you have a down dropping block in here that forms the trough with a flat floor shape. But my question is, like when we're in Hawaii and then like we just learn a little bit more about like how gravity and overburden pressure will change the mode from opening to sliding. So in such a small body, my question is, how do you have enough overburden pressure to shift all the stresses from tensile to compressive in order to form like big faults that you can actually see on the surface in here? So my hypothesis is that it is actually just open. It just joints that opens up, and later on, because you have smaller impact craters that hit and other processes that kind of filled in to the joints, and then form actually will be more like V-shaped or a bow-shaped type of structures that we see, basically just the opening itself. So to test it, it's basically first I'm looking into the cross-sectional geometry because they're different from flat floor and also like a V-shape shape. So, you know, we see it on Earth, a graben is more or less like a flat floor shape. And also on Moon and also Mars too, if you draw like a cross section around like Moon, you know, this is very, very flat floor, and then this is like very also flat floor to be more complex structures in there. And every time I have to remind my structural geology student that, you know, they don't really have like a lot of like erosion and weathering as what we have on Earth. So these structures actually last for like billions of years old. Like they're really old and they just stay there and preserved. So it's really amazing, which is what we will also kind of picture may happen on Vesta too, although there's like some impact craters, but we should still be able to see that. And that's what we see on Vesta. So of course we do more analysis, and if you're interested to look at each of the profile that we have, it's all published in here. But here I'm just showing you a sample of like a typical morphology of how it looks like. So we have maybe 1, 2, 3, and 4 main troughs along this section in here. So 1, 2, 3, and 4. And then we found that most of them is basically bow-shaped and V-shape. I think the number is around like 80, more than 80% is bow-shaped and V-shape. We do see some flat floor shape for the northern trough that is like older and also wider too at the same time. So that's what we think, that it's not usually flat floor shape, but more close to a V shape for a joint. And later on, we also look into the displacement profiles. So if it's a fault, then we will have the maximum sliding, the offset at the middle, and then taper towards the two ends. And it should be represented by the relief of the trough itself on both sides. So here is the data. So basically we have like trough 1, 2, 3, and 4. We get the elevation of the lower part of the trough and then the upper part, and then like basically just like what is the difference in between. And then we plot the difference along the length. And again, because it's a trough, so you have like both sides of the rim. So you have a northern one and also a southern rim too. But in here, what we found is, except probably only the northern rim of trough 2 had its maximum relief at the middle that tapered towards the two end, and then none of them, the other ones, show this pattern. And if you have a graben that with two normal faults that is like forming in the same system, their profile should also mimic one another because it's the same system. So where you will have the maximum peak will be the same for the other end of the maximum peak there, and then it mimics its shape. And we don't really find that system in here too. So the next, we're going to look into the joint. So the joint is more easier. So we basically just measure, what is the width of the trough and then plot it along the way. And because of time, I don't have the individual ones shown here, but again, it's all published. In here, what I'm showing is also another very typical characteristic for joint is that if you add them up like accumulatively for a whole system, they should show the same one. So for example, if we have the entire trough system, it's like around like 80 kilometers long. So from 0, at that point, we add all those width together for the 4 main set of trough and then plot it all the way along. And here we see that, and of course, like sometimes there's like covered by impact craters, so we don't get like some of the data that's shown as dotted line. If we see the overall structures of the pattern, you have the maximum width at the middle, and that tapers towards the 2 and 2. And if you look into the paper, like the individual ones also shows a very similar pattern in this way. So I conclude that the morphology of the defoliate fossil do not support a faulting origin, but it's consistent with a jointing origin. So that's basically what we are thinking when we understand how gravity works on the small body. That is probably you have like even bigger, more massive like joint. And then later on, if you go really deep enough, then maybe the overburden pressure will be large enough to have like normal faults to occur at depth. And we can actually calculate it. So the next part is basically a rock mechanical calculation to predict, okay, at this gravity, and I'm going to tell you some other parameters later on in this condition, at what depth we will expect faulting to occur. So the spacecraft data, we know there's core, mantle, and crust. We know pretty well for the estimate of like how big they are, the thickness, and also what is the density. And let me explain. So we have that information in here, so we can calculate how gravity changed from the surface towards the core, and then how overburden pressure changed from the surface, from 0, increase towards the core. And with that information too, we know, we estimate basically on Vesta, it's basically just like basaltic rock. And we know a lot of things about basalt on Earth, like the experimental data, we know what is the rock strength. So in here, I'm using a typical compressive rock strength in here, but like the number that we use is basically like lab experiments. So they are like intact rocks, meaning that there's no single fracture. It's just like a perfect rock. But in this case, it will mean that Vesta is just a one single rock intact without a single fracture, which is not really realistic. If you think about, you have those structures around, you have those two big impacts, right? It's already pretty fractured. So in here, we use a system that is very typically used in industry for the engineering geology called RMR. That's from 10, it means that it's 100, it means that it's an intact rock. And then when the rating goes towards the lower, it means that's like more fracturing in the system. And then when it's 0, that's basically a rubble pile. So like soil, you can just break it with your whole hands. So, and in here, that's basically the stress that you need in order for normal faults to occur. And we have the depth here from 0 at the surface, all the way to almost to the core. So in here, because the studies and then we estimate Vesta is a highly fractured asteroid. So we are taking our calculation from this side, and then that suggests that faulting can only occur at least 5 kilometers deep, but it can up to be like 55. It is not a range, it is the minimum depth that you will have. So depends on how fractured it is, it can be at 5 kilometers or it can be much deeper than that. So in this case, we think jointing, again, is a more presumable fracturing behavior in that sense. And not that it's not possible, because if you remember, when you have the relief, some of them is like a little bit above like 5. But in order for that to, as you can see in the surface, you must have a really big opening. That's basically the trough that we are seeing. So if you think about it, back to Hawaii, that's still like the very early stage when you have the opening and maybe some sort of faulting that start to occur. But the whole system is not a fault itself. So now we know, what is the fracturing type of this large scale trough in here. My next question is, so what are the processes and mechanisms that forms these troughs? So again, after the dawn, data is sent back, and there is a paper that studied what is the relationship between the geographic relationship of these troughs and also the two basins, because it's pretty fit with one another. So they basically, here is the South Pole, and then you have the Recipient Basin in here. They put a circle, so that's the center, and then the Recipient Basin here, they put a circle in here again, and they estimate this is the center of it. And they also mapped the Folia Fossae in white color in here, and then the Saturnalia Fossae in red color in here, and then plot it in the Asteroid. And then calculate, where their poles are. And it suggests that the Folia Fossae is concentric around the center of the Recipient Basin, and the Saturnalia Fossae is concentric around the Vananalia Basin. So what is proposed is that we have first the Vananalia impact hit, and then directly and simultaneously form this northern trough in here. And then the Recipient Basin hit superposed on top of the older basin, and then form the Folia Fossae just directly, like right after the incident. But is that true? So what my work is to study in more details about what are the actual relationship. So I did a geologic mapping. Basically, the previous one is from the previous work for the trough itself, and I mapped like the basin in here. I do a little bit more detailed work for the basin structures. If you're interested, the map is in this paper in here. But today we only focus on the location and the shape of the basin. That's very interesting information within the basin too. If you're into, like, for example, like landsliding and also some rotation stuff about like a small body, then you should also take a look at that. So we have the basin here first. So what I instantly, if I'm going to plot two things together, is there's a very clear cross-cutting relationship in here. Like this side of the trough is entirely lying within the basin. So here is the hill-shaped data. So you can see this is basically the basin rim in here in purple, and then this is the trough. So it is not documented before, but it's a very clear cross-cutting relationship to tell us like the Folia Fossae must form well after, not just when the impact crater hits, but after the whole basin is like modification complete. Because if you think about it's such a big impact, you need time for things to rebound in the center and then form the rim. Later on, I think there's numerical modeling work that suggests it could be a couple of hours. So like it's well after it formed. So it's a little bit contradicting with the time constraints that we have from the hypothesis. So the next I'm going to look into, so we have a first line of evidence in here, and the next I'm going to look into their geographic relationship, because that's the evidence that we have, or they're directly connected with one another. But I'm going to just look at the map itself. If you only look at the Recipient Basin, that's actually kind of offset from where you would think the set of trough is concentric around. But of course, you have to do a more detailed analysis. So here, I calculate the geometric mean center of the Recipient Basin because it's irregular. So, it's not entirely accurate. You just put a circle here. You have to account with how irregular the shape is. So this is the center of the basin. And then I calculate, because we have 4 main set of trough, I calculate where their poles are. And then I calculate where the 95% confidence interval. So if it's within the 95% confidence interval, we can tell that, there's like 95% probability they are actually in the same group. As you can see, the basin center is outside of that ellipse. So, my Another evidence is the defoliate fossae are not really concentric around the center of the reservoir basin, which is contradict with the previous study. So my question is, what are the next, what is the possibility? Like, how are they formed? And just by the data set in here, I realized there is this big depression, topographic depression, that is like around at the South Pole as a circle in here, not just contributed by the reservoir basin, but also contributed by the Vanadium basin together. So my next step is to calculate the geometric mean center of both basins combined. So that's basically the point where I would say, oh, this is the center of both basins of the shape. And then again, I plot the 95% confidence interval in it. And this time it is within the 95% confidence interval. So, and it's not just about the center of the two basins itself, but also if you realize the South Pole, which is the spinning axis, is also within the 95% confidence interval. Therefore, I conclude that the defoliate fossae is concentric around both the spinning axis, which is the South Pole, and also the center of both basins combined. So in here, I collect a series of geologic constraints that point towards maybe a spinning-related origin of defoliate fossae that could be a long-term consequence of both impact together. So here it's what is my idea, is what I think. So first of all, you have Vesta. We don't really know, what is the orientation of the first impact hit. So I'm just making it up, let's say it's at the equator. And then, so now you have this big impact basin in here that forms a negative gravitational anomaly. And when you have a spinning object, that tends to move towards the pole. So let's say this time it moved towards the South Pole. And then because of the fast spinning, then maybe some sort of, tidal bulging, because one spin of Vesta is 5 hours. So it's really, really quick. And then for the whole process, for a long-term consequence, you may have jointing at the equator. And then that is the Vanadium basin. But the story doesn't end here. So as we know, there's another large impact. There's the reservoir that again hits, and then this time is superposed on top of the older impact basin. So both of them create the negative gravitational anomaly. And then you have reorientation, maybe a very small one, because it's already at the South Pole, and then you add something on it, it could be a few degrees of reorientation, maybe some tidal bulging too, because it's still spinning really fast. And then as a result, you formed the new defoliate fossae that's concentric around both basins together with the South Pole, and also now the old joint, which is the Saturnalia fossae, is basically tilted. So now I'm working on with my collaborators to try to use numerical modeling to see if we have reorientation, and then we may change, some spinning at the rate of the upspin or despinning, can we produce what we saw in here? So what is the stress? Is the stress enough to form fracture? Is it at the equator at the same mode? So jointing, so it means that it must be tensile stress that's going from the North Pole and the South Pole. And then, yeah, it's the orientation, right, of what we saw in here. So if that's true, which we're working on it, that it will basically fulfill what we see about the morphology, the structures, and also their age relationship. So before I end, I want to go back to my big question is, how are structures formed on planetary surface without plate tectonics? In a more specific, what are processes, mechanism, and how are they different from what we observe on Earth? So on Earth, for the fieldwork part, we basically see how Earth's gravity controls the transition from jointing to faulting along the fault zone in Hawaii. And when we apply it to Vesta, we see that under the low gravity of Vesta, the defoliate fossae are basically large-scale joint that can be with or without a faulting at depth. And then we also see that the defoliate fossae has a spinning-related origin as a long-term consequence of the large impact. Although large impact, they form structures too, but they are not the only way to form structure. There's so many ways that sometimes may be indirect that needs to be considered. So that's basically my work. I'm just going to tell, in the future, really want to do a very similar work from Hawaii to Iceland to just see, if we find a very similar observation. We're doing some fault scaling projects in here, so it will be really nice to see if we can get the same fault scaling that is like representable, or like if something is different, then why? Like what are the conditions? Like it's different. Maybe it's the rock type, maybe it's a tectonic setting, but we have to do the work. And what I've done for Vesta can definitely do for other smaller bodies, which will be really cool. And especially we have some space mission that is going to smaller bodies too. And knowing about the rock mechanics is important if you want to get samples from there too. So that's another important part. And as mentioned earlier, like my old work is basically for Venus tectonics, and here is some project that I'm currently working on or want to work in the future. If you're interested, so please let me know. And that's it. I'm happy to take questions.